Thank you very much for joining me this afternoon. So I'm a mathematician. I'm also French. I'm not sure which one of the two will be more convincing at the end of the talk, but you will learn a little bit about math, a lot about the French accent, so I apologize. I wanted to ask this question: can one truly understand by counting? And let me make you a promise, is that I will not answer this question during this talk. Okay? So why do I ask this question? Because one of the most common question or comment that I'm given when I give public lectures is, people arriving to me and saying, "Oh, I was terrible at math. I know nothing about math." And not that I hate this answer, but I always want to answer the same thing. So let me tell you by first asking a question. To your opinion, a 3-year-old, actually this is maybe not a 3-year-old, but a 3-year-old, to how many can he or she count? Like have a notion of number. You can raise your hand, give the number. I will repeat for the people that will be online. A 3-year-old knows how to count to what? To 10, to 5, to 100. Yes? 50? 50? Wow, that's a very clever 3-year-old. Good. Other, try, I don't know, less than 50. More, who think more than 50? Because I don't, wow, okay. There were less than 50. Okay. 10. Who think 10, roughly? Okay. Less than 10? We can start recognizing the parents. Okay, 5, right? Less than 5. Good. So he knows my kid. So a 3-year-old basically has a notion of number up to 3. I'm saying 3. Of course, my daughter knew how to go up to 10, but it's just a sequence of words. She doesn't have the notion of what is 7. And in some sense, the most surprising thing, so basically the kids start to get it between 3 and 4, 5. That's exactly the range. That's why I ask for 3. But just for you to realize, if I ask you now a toddler, like really a baby getting out of, in the world, to how many can he or she count? Yes? 2? Who thinks 1? Who thinks more than 3, but nobody? Nobody, okay, good. Who thinks 1? Okay, 2? 3? Oh, many people didn't understand that this was, you had to answer one of the 3, right? Well, anyway, okay, so why not? So there were more 1 than 2, more 2 than 3s. Well, it basically knows how to count to 3. They are very, very interesting experiments. You put some kind of objects behind a curtain, something that is hiding, and then either you put it up and it's the right number of objects that you put, and the kid doesn't really react. But if you remove, being hidden, you remove some objects, or you add some objects, the kid will be surprised. Like they have ways of measuring, and this is for kids that are like 2 hours old or 3 hours old. So in some sense, at age 3, kids didn't learn to count much better than when they were born. Animals have a notion of number. It's not, but they have a limited notion of number, exactly like our kids have very limited notion of numbers when they are born. So there is something innate. Of course, we come up with some kind of notion of number, but it's an approximate one. And what makes the difference between human and animals is that we do get through our education a notion of bigger numbers. We are able to compare 11 and 12. We know that 12 is larger than 11. An animal will have no ability to make a distinction between these numbers. So numbers are something that we know. It's an ability that we learn, and so nobody is bad in math because most people know how to count. Okay? And so that was the starting point of my talk, is just to first make this point. By the way, it's not something that is that old. It's basically coinciding with writing or things like that. They are the Ishango bones that are found in Congo. They are 20,000 years old, and they are one of the first proof of enumeration by human. But again, like it is a very complex notion, numbers. And counting is an ability that is not, we are not born with it. We learn how to count beyond this very simple 1, 2, 3, maybe up to 5, etc. Okay, but if you start from this thing, then there is a kind of second question that the person asks is like, okay, well, okay, I know how to count, but I know how to count poorly, and you are great at counting, right? You can count up to very large numbers, or you can multiply very big numbers together. I mean, a mathematician at the end is just somebody good at multiplying or counting, right? And so what I wanted to show in this talk is that we are a little bit more than that, hopefully. I would even say that I'm a good mathematician because I'm terrible at counting, but that's another point. So let me try to tell you a little bit this story of what can happen in the head of a mathematician, starting from maybe a counting problem to just go in the direction of this person that is speaking to me, but showing how this is just the beginning of the story, that in fact in mathematics we are interested in what is next to that. And since I'm a probabilist, I'm going to use randomness and random things to justify, to kind of tell my story. So first thing, maybe, so random is just, let's be all on the same page. A random thing is something we cannot predict, okay? There is no ability to predict. And there are different kinds of randomness. In particular, there is there are different classifications as well, but there is one distinction that I like very much. It's between what we call mild randomness and something else that I will tell you soon. So mild randomness is typically the following. Imagine I want to count, like to evaluate in this room, what is the average size. I would have, I want to understand what is the average size in England. I'm gonna, take maybe this group here, look at the average size here, and it will give me a very good estimate of the average size of the whole room, a very good estimate of the average size in Oxford, a very good estimate of the average size in United Kingdom. Because we kind of, even if the tallest person enter here or the smallest baby, it's not going to change much the whole average size of the room, you agree? One individual instance of randomness, I don't know what is the size of the person entering, is not going to change much the outcome. This is typical for mild randomness. And mild randomness is something that we encounter quite often when we are trying to estimate what is, the chances that A is going to be elected or B is going to be elected. You see, I'm very politically correct. You can do this test on very few groups and then get some statistics and some chances of A winning or B winning. So here counting is very good. You take a small group, you count number of people that want to vote A, and you divide by the total number. It gives you a probability, and it's going to be a very good estimate of the probability that A is going to win. If you don't traffic, of course, and change the things to try to adapt to your need, which is quite often what happens with these tests. But there is another kind of randomness. Imagine I ask you the same, we play the same game, but I try to look at the average wealth in this room. Okay? How much people own. There it's going to be much more complicated, because if Elon Musk enters in this room, you do agree, I think, I don't know exactly who is in this room, but probably the total wealth of the room is going to change by an order of magnitude. One individual person may change totally what is going to happen in the result. It's like the result is governed by extraordinary events. And this is something that Mandelbrot, the father of fractals, noticed about finance. Finance, which is one of the fields where the mild randomness is used the most. People are basing the study of finance on stochastic calculus, things like that, that are very good suited to mild randomness. But he said, no, there are things like cracks and things like that that actually resemble this wide randomness, where there is suddenly something that breaks down and things change way more rapidly than they should for mild randomness. And in particular, the tools that people usually use, here I just mentioned them for the mathematician in the room, like that I can see who is like, so this, I know these are the mathematicians. The normal law and the variance, for instance, are things that do not work at all for this much more brutal randomness. It's the same randomness that you will get with an epidemic, for instance. You cannot predict when it's going to happen, and when it happens, it changes completely. The forest fires, we see that in Los Angeles those days. Same thing, you cannot predict, etc., etc. The earthquakes, all these things are typical instances of wide randomness. And so in particular, when people come to a mathematician, a probabilist, or a statistician and say, why cannot you predict these kind of things? Well, the easy answer is like, well, this is wide randomness. I mean, how can I understand or find out that an epidemic is going to happen exactly at this time and not 2 years before or 2 years later or 10 years before 10 years later? So this wide randomness is much more difficult to predict. But it's also, I mean, of course, when it's difficult, it's also much more mesmerizing and interesting. So what I'm going to tell you about is an example of something that exhibits this wide randomness. It will not be totally clear why it's wide randomness. I will tell you exactly at the point what is typical from wide randomness in it. And this example, you are going to see, it's cool, or I find it cool, I should say, because it starts from a counting problem, but it goes far beyond that. So I think it's a good example for what I want to tell you. So, wide randomness in the context of polymers. So the goal is the following. I would like to understand mathematically what happens in very long chains, like proteins or molecules that are made of many constituents and that are very long. Okay? It's like DNA or things like that. And I'm going to make a mathematical caricature, if you want, of what happens in a polymer. And what is the simplest caricature is that this polymer, I mean, it's not that big, but I mean, I'm trying to make it at your scale. This polymer is made of many constituents that are glued together in some sense. So what I'm going to do is the following. I'm going to assume that they are measured or they are drawn as safe-avoiding paths. So what do I mean by that? Don't panic. I'm going to choose what we call a lattice. A lattice is what? Is just a paving, for instance, by squares. It's like you are in your kitchen and you have squares on the floor. This is the square lattice. You are the proud owner of or renter of a square lattice. Let's be careful. On this square lattice, I'm going to start from one intersection, one place. So here, for instance, I'm going to start from there. And I'm going to draw a path on this lattice. So I'm just going to follow the edges of the squares, just step by step. And I'm going to imagine that each step of this path is kind of a monomer, like an element of my polymer. And they are kind of connected by what we call sometimes the bond, but just the boundaries, the edges of these squares. Okay? And I'm going to assume one more thing, because for now it's not a great model for polymers, because you kind of guess that two places of my polymer cannot be exactly at the same place. You cannot superimpose two molecules, or two parts of a molecule. So I'm going to ask that the path is safe-avoiding, meaning that it never comes back to the same place. Okay? So like that, each one of my monomer has its own place. It's nice. And is it clear for everybody? Whoa, many people said yes, that's good. I'm going to go with, or maybe I just saw the one that was saying yes. Okay. And the question is actually not such a crazy question. Is imagine that I take a long such object. How does it look? That's the first question you can ask on this thing is, how does it look? If I take a long thing like that, is it typical that it looks like a straight line? Does it have a tendency to, maybe stay very close to itself? What happens? how does it look? Exactly like a DNA a molecule, how does it look in our body? Okay, so there is one case where we can answer this, is if we relax, we just forget about the self-avoiding property. Just forget. Maybe if I forget, I get the right answer. So let's just forget about the self-avoiding property. And the good thing with forgetting is that if I tell you I want a path of a certain given length, like 1,000 steps, if I totally forget about the self-avoiding property, I have a way of sampling one fairly easily, which is just I'm sitting there, I choose one of my 4 neighbors at random. I don't know, I have this dice with 4 edges, let's say, I throw it. Depending on the result, I move to one of my neighbors, and then I pick again my dice, and I do it again. And I do this, okay, I should be careful, 999 times. Okay, do not judge me on this one. I told you I was bad at counting. And I do that, and I just measure where I am. What's the distance to the origin? And there is a famous result. It's actually not very difficult, but definitely too difficult for this thing, that you are typically at distance 1,000 to the 1/2. And if I would have done 1 billion step, it would be 1 billion to the 1/2. And if you can imagine a bigger number, it would be a bigger number to the 1/2. So it grows, it increases with the length, which is kind of natural because you have more and more possibilities. And it increases like the square root of the length. So now there is a natural question, and I'm going to ask you all. Now, if I do not forget about the self-avoiding condition, do I also get like that? Who thinks yes? I realize that, okay, maybe I should ask first, who doesn't want to answer this? Just that, okay, no, so nobody thinks yes, that's good. Who thinks no? Everybody else, thank you. At least I will teach you something during this. Okay, so if you do not think it's 1/2, what is your prediction? Don't worry, there is no, mark at the end of the, I have terrible facial recognition, I will not remember you, don't worry.
Further away.
Further away, I do agree. That sounds like a natural thing. How much farther? Do you think it's going to be roughly n? Meaning that you would basically go in one direction, and in some sense it's not that unreasonable if you think about it, because you want to kind of avoid your path. So it's kind of like there is something that you really want to avoid. Maybe you go in one direction and you basically to distance n. So I saw several people doing, yeah, you would be convinced by that? No? I'm not sure what. Okay. Okay, so it's not n. So if maybe I interpret what you say is that you are still going to turn, roughly. That's what you want to draw. So if it's not n to the 1/2, what can it be? What is your prediction? I have, the whole day, so if you don't answer. If it's not 1/2, if it's not 1, yes?
N to the 1/4.
1/4?
Yeah.
So 1/4, n to the 1/4 would be less far than, right? I mean, n to the 1/4 would be smaller than n to the 1/2. So that maybe with the self-avoidance, it feels like it should be pushing us away. So let's try to find a number between 1/2 and 1. There was another person raising the hand. Yes? N squared. Well, that's a very so n. So n squared means that okay, it's large steps. So no, it has to be smaller than n. It's n steps. Okay, between 1/2 and 1. Yes. 2/3. I'm never going to manage this one. Yes, that was not bad, but it's not that. Yeah. 3/4. Okay. Congratulations, we have a physicist in the room. Congratulations. So it could have been 2/3. It was 3/4. And this is a prediction. It's not proved. So it's a conjecture. We would like to prove that, but we don't know. And just for the small story, so this is a randomly sampled self-avoiding walk. We see that it's much less packed than the random walk. And just for the story, so this prediction of n to the 3/4 was made by Paul Fleury in the 50s. He got the Nobel Prize in chemistry. He was so at the time, one has to say that many theoretical chemists were basically mathematicians. So I mean, don't tell them. I mean, fortunately, they are not really here to listen. But they were really very strong in math. And so he made this prediction. But I want to tell you something about this prediction, which is interesting, is that you need to be very good to make a right prediction. It's something not easy, and for instance, it's not something I'm very good at. I'm better at proving things or seeing like the architecture of a proof than at guessing what should be an answer. Some people are, on contrary, extremely good at guessing. But so it's difficult to get the right answer, but it's really, you need to be a genius to get the right answer by making mistakes. And in this case, Paul Fleury did manage to get the right answer by making 2 mistakes on 2 statements. He assumed 2 things on the self-avoiding walk. Both are wrong, but what he got was right. So for the young people in the room, do an even number of mistakes. It's really important. That's yes, okay. So fantastic prediction for completely wrong reasons. But this is the right answer, and as a mathematician, when you get this, and in addition, you don't have a good hint why this is true, it's really mesmerizing. Like it asks for an answer. So this was about the geometry in some sense, the random geometry of this thing. How do they look? But there is a question you can ask, which is even simpler in some sense, which is, how many are there? How many walks of a given length can I find? So let's come together. And since you love to answer my questions, I do not feel I'm going to be alone on this one. It's going to be a very long talk. So let me give you part of it. So if I take a walk of length 1, meaning with one step, okay? With 0 steps, sorry, with 1 monomer. There is only one, right? There is just 1 monomer somewhere. Now if I ask you, walk of length 2, meaning with 2 monomers. So 1 edge and 2 monomers. How many walks like that can I do? I'm somewhere, I need to do 1 step. How many possibilities do I have? 4. Very good. So C2, the number of walks with 2 monomers, is 4.
Why is that 4?
Sorry?
Why is that 4?
Why is that 4? Because I have 4 possibilities. I can go up, I can go right, this right, left and down. So I have 4 possible drawings.
Rotations and symmetries, isn't it?
So I didn't say count up to symmetries. So you are right that if I would be, in some sense, each one of them is just the image by a rotation by a right angle. But this is not my question. I'm ready. You are allowed to count things, you know, I mean, just they are different. This walk is not the same as this one. And it's not the same as this one. Even this one is even a reflection also, but these are different. Okay? Different walks. Just you start from 1 point. That's the only thing. So, sorry? Because it was length 1. So I can just go to the neighbors. Very good, very good. Because this gave also time to the others to think what is now with 2 steps. Let's go for 2 steps. Oh, people did think during the beginning. Yes. So who thinks 12? Who thinks 16? Aha, I got you. 16, I guess, is because you thought that I asked how many walk, which was true. I meant how many self-avoiding walks. So I have 4 steps for the first step, but for the second step, if I'm asking to be self-avoiding, I'm not allowed to go back to where I was. Now I have only 3 possibilities. I cannot step back. This would be stepping on my past. So I have indeed 12 solutions. 4 monomers, 36. Very good. Very good, yes. 5? It becomes more complicated. Huh? Alors, okay, that was a French word, alors, which means, so I heard 108, and I heard 100. So 108 is 3 times 36. Yes? I'm checking because, yes. Why thinking that? Because, well, you know, after 4 steps, I still have 3 possibilities, right? This sounds very reasonable. So for the people that thought 108, why it's not 108?
You might end up feeling one is supposed to count.
Exactly. So, of course, you need to avoid your previous step, but you need to avoid your whole path. And in 5 steps, I could be doing this, 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 and here, if I'm here, I cannot step here, but I'm also not allowed to step on my first vertex. So this walk is forbidden. And by the way, this one also, and this one also, and in the other direction as well. So I need to exclude 8 walks out of the 108. I get 100. Okay? Very good for the people who thought 100, sorry. And, okay, if you keep going, you will say that C6 is 284, and then it starts to become a little bit complicated because you need to see all the possibilities to restep on yourself, so it starts to be really not so easy. I do not recommend that at home. That's not a good exercise, but you know, sometimes the internet breaks down, so you have to. I can see the young people like, no, internet. Okay, and if internet breaks down for a very, 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 very long time, you can get to this result. So if you look at walks of length 72, this is the number. And just for the anecdote, I was giving this talk in front in a hospital, in front of all the doctors in the hospital, and somebody said, "Oh, it's funny. It's roughly the order of magnitude of bacteria on Earth." So now you learn something. There are many, many bacteria. You know, I didn't check the thing, but I find it so great. So the person was like, "Of course, number of bacteria." Well, since then, I use much more. Anyway, the interesting thing with that is not so much the numbers, and C72, you really get it. So of course, it's not by hand. No mathematician ever will be able to compute this by hand. What happens is that with computers and very clever algorithms and a lot of computing time, you manage to this. And just to tell you, we don't know C73. Because if you think about it, even the knowledge of C72, so number of walks of length 72, gives me very little information on how I can add 1 step. Because there are such walks where I have 3 possibilities, because maybe I arrive straight. There are some walks where I did exactly a roundabout and I cannot have to avoid a second place. And in fact, there are even walks, if you think about it, that spiral like that and end in such a way that you cannot add 1 step. It's impossible. So it's a very difficult computational problem. But out of it, you still learn something, that when you do the ratio, you look at how fast it grows, it seems that there is a rate of growth. It seems to be roughly multiplied by 2.638. It's funny, but it seems like that. Okay. Keep this in mind, or forget it, it's fine. But and let's do one more time, because I'm having fun. I don't know for you, but I'm having fun. So let's do it on another lattice. Why? I mean, you know, maybe your kitchen is not made of squares, and I don't want you tonight to feel like you were, considered as special. So if it's made of hexagons, you can do the same game. So I give you C1, still 1 walk. C2 now, it's what? 3, right? There are 3 steps now. C3 is 6, right? 3 steps for the first, 2 for the next because I'm not allowed to backtrack. C4 is 12, C5 is 24, C6 48, C7. Aha, yes, you got it. C7, there starts to be a problem of making a loop. So it's not going to be 96. You have to remove the cycles, and there are 6 of them. So you get C7 is 90. And if your internet breaks down for a long time, you can get to C106 and get this huge number, which I will not compare to anything depressing, I promise. But again, you can do the ratio, try to look at the rate. And the rate, in this case, gives you something very, very surprising. It gives you this number, square root of 2 plus square root 2. And for the story, this number was predicted by a physicist, Nienhuis, in 1982. So it's before I was born, so I consider it as old. And just for the story, if you think that theorems in math, even modern theorems, are necessarily not comprehensible, maybe I will actually convince you that you were right. But just to tell you, this is now a theorem, and it's from 2012. That's not the person, actually. I just forgot that I removed another picture. So it's a theorem exactly by me and my supervisor, Stanislas Smirnov. So in 2012, 30 years after the prediction, we prove this result. And what is funny for people that use ChatGPT all day long is that, of course, in AI these days, people are trying to convince mathematicians that they are going to be replaced very soon, which we are a little bit afraid of that. But one day like that, I thought, oh, I'm going to ask, what is the value of what we call the connective constant of the hexagonal lattice to ChatGPT. And the ChatGPT gave me 2.632. I was like, it's funny because I think I know this number, and this looks very much like the connective constant of the square lattice. And the person said, ChatGPT said, because I'm always thinking it's a person, but it's so polite at the end. It tells you things wrong, but in a very polite way. And the ChatGPT just answered, no, the connective constant of the square lattice is square root of 2 plus square root of 2. Like, I can assure you that I think you are wrong. And they're like, no. Well, so then I take a screenshot and send it to Stas saying we have a few years in front of us. We will not be replaced by ChatGPT at least. Well, so anyway, it's square root of 2 plus square root of 2. So, we started by a counting problem. And in some sense, we already evolved a little bit by looking at this rate of convergence, which is still related to counting, but not entirely just counting. But now, let's look at this person, Thurston, one of the greatest mathematicians of the 20th century, and also even beyond, I would say, the beauty of the math that he did. It's somebody that really had a vision of mathematics, which is very instructive. So I recommend reading in particular his essays on what is mathematics. And one thing that he mentioned in his most classical written essay is that he mentioned the case of people that are discovering, are finding the 10,000 first prime numbers. 2, 3, 5, 7. I'm going to stop there because I'm going to, of course, cite something that will not be a prime number, and then it's on YouTube, and people are going to be, this medalist doesn't know his prime numbers. But what he is mentioning is that people, when they do that, it's also some kind of counting or checking, on they discover that that's not what they are seeking. They are not seeking at knowing the 10,001 first, 10,000, wow, I don't know how you say that in English, but the next prime number. What they want is understanding. They want to understand how these prime numbers behave, why they are this number, blah, 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 blah. And here it's the same. Counting self-forwarding walk, it's not my passion. I don't care. When internet breaks down, I do not count self-forwarding walks, of course. But I saw that you were like, maybe it's going to fall. Anyway, what I want is to understand what these numbers tell me. And they tell me something very interesting, well beyond the fact that it's cool to find square root of 2 plus square root of 2 because, well, that's a fine number. They tell us something more, is that, in fact, when you look at this number, not only it grows like an exponential, but you can try to approximate it a little bit better, to really get a better estimate at what happens. And what you find is that in front of the 2.632, there is a power, n to the 11 over 32, like everybody guessed, right? People that didn't guess that, out. So this is on the square lattice. But if you do it on the hexagonal lattice, I told you that the rate of increase is not 2.632, it's square root of 2 plus square root of 2, which is like 1.84 roughly. So it's not at all the same rate. Yet, the correction in front, it's n to the 11 over 32. So really imagine like one is a number of bacteria in the universe, the other thing is much less than that, and still the correction in front, it's the same. That has to tell you something. There is something hidden there. The numbers, the counting, give you an information that goes well beyond just, well, what is C72. And if you would do it, you know, for people that were like, he still didn't get how my kitchen is paved, for people who have triangles in it, you can play the same game. You will get a rate of growth, which is much faster, and still the correction in front, n to the 11 over 32. At least the first time I learned about that, I was mesmerized. I was like, how is it possible? Like, what is happening that you get so different numbers, but they have such a similar structure? And 11 over 32, I mean, come on. So just to remind you, these are really totally different numbers. So this thing is huge compared to this one. Huge. It's absolutely not the same number. The correction is the same. And here, what seems to be going beyond numbers is that there is some kind of lattice-independent structure, something that does not rely on the lattice. So as a mathematician, we are going to go seek for that. And the way to do it is to try to make the lattice disappear. And I'm going to do it by looking at a lattice, at a paving by squares, but smaller and smaller squares. Okay? Of course, if I want to still see my walks, I'm going to have to take longer and longer walks, because if I look at a walk of length 10, but I look at smaller and smaller squares, on my picture it's going to shrink to 1 point, right? So I'm going to look at longer and longer walks, just adapted in size, that I always see something funny. And doing that, I'm going to leave the world of self-forwarding paths, of counting, of my lattice, and I'm going to enter in a completely different world. And this different world, it's a world of random fractals, the world of fractals. So this is an example. So at the limits, when you shrink the lattice to that, in some sense, it almost vanishes, appears something much richer and much more beautiful in some sense than the original drawings of walks, and it's fractals. Of course, I'm not justifying why, simply because I don't know, but that's what happens. So just for people who do not know what fractals is, it's fine, everybody. So a fractal is a self-similar thing, something where when you zoom, you see the same thing. So this is a typical example. It's a Van Gogh snowflake. And you see, what you do here is that you repeat a process which is adding always a triangle in the middle of each face. Okay? And you repeat it up to infinity. And if you do it up to infinity and you start zooming on one edge, you are going to see something like that. The more you zoom, the more you see the same thing. You can keep zooming for a long time. You will always see this recurrent pattern. This is a fractal. Okay? That's beautiful, no? It's not from me. I didn't make this picture. Just to show you a bit of fractal, this is the Mandelbrot set. And so this is, I'm not going to explain to you how it's defined because this is not mattering, but you see, the more you zoom, the more you see repeating patterns, etc., etc. So just for it's also a teaser. because you have actually videos of hours of zooming on the Mandelbrot set. I realized, there are people counting safe-forwarding walk up to 72. There are people making like 4 hours videos of zooming on Mandelbrot set. The world is a beautiful place. And in addition, usually there is psychedelic music. So you kind of guess why they are doing that. But so anyway, so this is a fractal. I wanted to show it to you because it's a beautiful picture. What's the connection with our safe-forwarding walk, or what do we learn from it? So, as I said, if you start from your safe-forwarding walk and you make the lattice shrink, you end up at the very end with a limiting fractal. What did you gain out of that? That's a question. What did you gain? What is special? I mean, why do mathematicians love fractals? I think mathematicians are like, oh my God, why do I like fractals again? Is it because I love this music? Because fractals are symmetrical. There is a lot of symmetry in fractals. And science in general, it's not something special about math, but the science is in some sense the art of finding structures, of finding symmetries in nature. The more symmetric an object, the simpler it is to study. And there is always this example that I give to parents. So there are some parents in this room, because I rediscovered it with my daughter. So it's this game, right, where you put shapes. I mean, normally it's your kid who is doing it, but you know how kids are. They're like, do it my place. But so you are supposed to put shapes in holes, right? You have a square, a triangle. And from your point of view, what is the first shape that kids manage to handle in this game? Who thinks squares? Good. Who thinks triangle? Yes. Who thinks disk? Okay, good. So a majority of people say the ball in the disk, and they are right because that's the most symmetrical object, right? It's the object that whatever, I mean, as soon as you found the right hole, you are going to manage to do it, right? Which is usually also why parents hate this game, because the first time my daughter played this game, she took the ball. I was lucky on this one, but she took the wrong hole, right? And her answer to the fact that it was not fitting in was just to hit harder on this poor box. And I was like, oof. Not sure that I manage well up to now, but there is a long way before she becomes a mathematician. So yes, the ball is the most symmetrical object. So in some sense, if you think of what is a mathematician, just think as a kid who didn't really grow and still try to find as many symmetries in nature, because the more symmetric the object, the simpler it will be for him to study. Of course, symmetry is taken in a general sense, maybe a little bit more abstract than what you are used to with like central symmetry or actual one, but it's really the idea, finding as many symmetries as possible. And this limiting fractal, it has a very good taste of being very symmetrical. It has a lot of symmetries. But because you have a lot of symmetries, I can study it very well. And I can say many things on it. And in particular, and I will finish on that, I can measure something which is called the dimension of my fractal. So dimension 1, 2, 3. This is knowledge that usually people get very well from childhood, which is incorporated in their brain. But dimension can be actually non-integer. It could be like 3/2, 2/3, 3/4, 4/3, etc., etc. So let me tell you what I mean by dimension, because clearly, it doesn't seem to be the same as the standard dimension. So if I take a segment like that, and I try to put little squares on it. If I put, let's say the segment is length 1 meter, and I try to put small squares of size 1 centimeter, how many do I need to cover the line? 100, right? If it was 1 millimeter, how many would I need? 1,000, etc., etc. If it was of size 1/n, I would need n of them. Now, if I do the same with a square, how many squares of size 1 centimeter do I need to cover a square of side 1 meter? 10,100 squared. If it was 1 millimeter, it would be 1 million. 1,000 squared, etc., etc. So here we see 2, which is a dimension of squares appearing, and we saw 1, which is a dimension of a segment. You would do that in a cube, it will be to the power 3. And in fact, if you do on the Van Gogh snowflake and you count, it will be n to some power, which will not be 1, which will not be 2. It will be something else, and in particular, also for the fractal that you get, you will also get something different. So for the Van Gogh, it will be log 4 over log 3, and for this limiting fractal that you get out of self-avoiding walk, it will be 4/3. And the 4/3 is related to the 3/4 of the dimension. So because I am in the limit, because I'm working with this fractal, and because this fractal has a lot of symmetries, there I know how to say many things, and I can in particular measure its dimension, and its dimension will give me an information on the self-avoiding walks. So seeking for symmetries. And that's basically the, let me just jump one slide. This is basically what I wanted to say, is that much more than counting, something that unifies mathematics is the quest for symmetries, for structure in objects. So beyond, you cannot understand everything by counting. It's kind of a hint. It's like you start picking by the window, and on the other side there is a world of mathematics with all its symmetries and all its connections between different objects. So the symmetries is really what you want to seek for. And just as a summary of the thing, counting is a way to get into understanding what could be the hidden structures, and then you go for these hidden structures. And one tool that really is used in basically all fields of mathematics in very different ways, because symmetric is a very generic term, is seeking for symmetries. Mathematics is the art of symmetries in some sense. So the more symmetric, the simpler. And let me finish by thanking you and showing you just one thing, and I let you think about what this is. Thank you very much.